So good afternoon, CGIL. This week we are happy to have Dr. Doug Bjelland presenting for us. Dr. Bjelland is a quantitative genetics consultant with Abacus Bio based in Edmonton. He obtained both his master's and PhD degrees from the University of Wisconsin-Madison in dairy cattle genetics. He has also spent some time as a postdoc at the University of Colorado and as a research geneticist at Alta Peak Genetics. His work has spanned various genetic
We can't hear you anymore.
Sorry about that. For some reason, the room disconnected. Sorry. Doug is particularly interested in the intersection of genetics and economics in animal agriculture, specializing in selection index development and nucleus herd management. Additionally, Doug has extensive expertise in dairy crossbred planning, breeding program design, genomic inbreeding, and relationship management, genomic software tool development and testing, and genomic breeding value pipeline development. And today he will be presenting global trends in selection indices. So you are welcome to go ahead, Doug.
Thank you, Gabriella. Yeah, thank you all for attending, and thank you, CGIL, for the invitation for Abacus to present. Really appreciate that. So to start off, I will just give a brief background on Abacus Bio as a whole. So we are an independent consultancy group, basically specializing in animal and plant genetics, and especially where that genetics intersects with economics. We work all across agriculture, in animal agriculture, crops, plants, forestry, aquaculture, even into insects. Been involved, not me personally, but others in a lot of different projects with bees. Currently about 50 plus people in our organization, split between our main office in New Zealand, another major office in the UK, a recent addition up in Edmonton here, and then also a brand new office with currently one person in Australia. So the logos you see on the screen are a handful of the groups and organizations that we work with. Basically anything from universities to large multinational agriculture organizations such as Bayer, work with a lot of breeding organizations, Angus Association, Red Angus, Holstein, Canada, things like that. Also governmental, non-governmental organizations, Dairy New Zealand, Dairy Australia, and then all the way down to working with single farms, single producers, especially in our New Zealand office where there's a lot of work with basically farm consultants. So what types of works do we do? Basically anything related to genetics or economics in agriculture. Breeding strategies, genomic evaluation, genetic evaluation, whether that includes genotype information or just pedigree information, data analysis, strategy, pipeline building around any of those related fields. A big part of our work is trait prioritization and selection index development. Also work with program evaluation audits. We have a mating program that's mainly used in sheep and beef in New Zealand, with a bit in Australia and in the UK. Then the bottom three on the right gets into the more strictly economic scale, do market assessments, things like milk pricing, modeling, and other aspects like that. Strategy, value chain assessments, some of that has been done with some of the beef slaughterhouses, and then starting to get into more of that whole farm systems area. But the main aspect and main part of our work that I'll be talking about today is selection index and trait prioritization. Here we have a timeline of work that Abacus personnel have been involved in throughout the years. A lot of work in beef, sheep, dairy, some in pigs. And then as you can see in more recent years, stretching out into more crops, different species such as goats, things even including coffee. A lot of the work in developed countries, with the main office in New Zealand, a lot of work there, and in Australia, UK, and starting to get more in North America, but also do plenty of work in developing countries. You can see several African countries listed on the slides, Ecuador. Other projects have been done in India and the Middle East, and hoping to get some more selection indexes within India and a couple other developing countries as well. So now to get into the more main topics, main points of my talks today on selection indexes, basically talk a little bit on the background of selection indexes, and then look at some trait additions and focus selection, kind of just some trends that we see in work that we are doing, as well as other developments around the globe. Get into some specifics on dairy beef, and then to touch a little bit on emissions impact. So a lot of this will be a little bit more dairy focused, as it's my background, but we'll touch into a few other species as well. So to start off, what is a selection index? Why do we need them? So essentially, selection index is just the result of geneticists and economists trying to select for multiple traits at the same time. So basically any species, dairy, beef, fish, bees, when we try to make genetic progress, we don't really want to just select one thing at once. We want to try to select for multiple traits at once. And when you select for multiple traits, you need to account for the economics that impact each of those different traits. You need to understand the heritabilities of each of those traits, you need to understand how those traits interact with each other, their genetic correlations, with a lot of those that can be antagonistic. So selecting for one trait, such as milk production, may hinder other traits such as health, fertility, things like that. So basically what we do with creating selection indexes is, you can see the formula on the bottom slide, or on the bottom portion of the slide, that selection index's goal is just a single total merit, single value for each animal, each line, each tree, whatever we're interested in. That formula is encompassing with a value per unit change in a specific trait that we're looking at. So in that first one, it's a calculated economic value for a growth trait. So a 1 unit change in growth trait would equal X value. Do things with like X unit change in feed efficiency. Same thing with, say, a meat quality trait. Try to get an economic value for a 1 unit change in the meat quality trait that we're looking at. Heat tolerance. You could think of any other trait that we're interested in for fish, cattle, whatever species. So to go into a little more detail in that formula. So here it's written out just a little bit different, but those V's still represent that economic value. And when we try to determine those, the biggest thing that goes into those is basically the bioeconomic modeling. And I'll provide a couple examples in the next slides, next following couple slides. But basically that's just looking at, we have a trait, a 1 unit change in that trait. What is the economic impact of that 1 unit change? Another thing we're interested in is a fancy definition called a discounted genetic expression. So this is just a kind of formal way of saying that we want to make sure the economics and the traits are put on the same scale. So one example I like to use for this is in beef cattle. If you take a trait such as, say, calf health, and take another trait such as marbling score, that calf health is going to be expressed as right away in that calf's life, but the marbling score is going to be expressed in, you see that, realize the value from that 18, 20, 24 months down the line when that animal's slaughtered. So when we're making these models, we want to make sure that those traits that are expressed extremely early and can have enormous impact down the line get a little more emphasis and a little more weighting. As you can imagine, if calf health is really poor, that calf dies, well, then they never get the chance to express those carcass traits. Another example can be trying to distinguish between traits that happen once, like that calf health trait, versus traits that happen multiple times, like a milk production trait in dairy cattle, or milk or mature weight in beef cattle. Something that each year when they have a calf, that genetic expression will happen. Another factor within the economic values that's extremely important with an abacus is making sure that those economic values are realistic and acceptable to the producers, to the AI companies, to whoever is going to be using these indexes in their final state. So we do this with extensive industry consultation, whether that's with board groups, producer panels, making sure that what we have makes sense. I think it's easy for scientists, us to just kind of get the data and say, here's a result, that's what it should be. But if that result isn't seen as realistic to producers, it's not going to have the benefit that we need it to have. Surveys are another big thing. Working with our biggest clients, definitely like to push gathering information, making sure we and they both understand what their clients are looking for. And then index testing. This includes looking at the expected response to selection, how these different traits play off each other, those antagonistic or potentially working together effects might have on the index. So all of these come into play when adjusting those economic values. And then the GEBV portion here just represents anything that could be a PTA, breeding value, and EPD, could be used genomics-based, pedigree-based, could just be a precision phenotype that's not gone through all the complications to get actual breeding value, could just be novel traits that we're simulating. Anything like that could be included in that GEBV portion. Generally like to keep that consistent within the index we develop. So getting into an example of calculating economic value. So this is a very easy, straightforward example looking at calculating an economic value for milk protein and milk fat. So when looking at this, basically we have, when there's a 1 unit change in, say, milk protein, what is the value, the extra value that a farmer will receive? And then with that, what is the extra cost that will be incurred with that 1 unit change or 1 unit gain in protein? So an obvious value is that the farmer will receive more in a milk check for a 1 kilogram, 1 pound increase in milk protein produced. But with that 1 kilogram, 1 pound increase in protein produced, basically a cow usually needs to eat more to reach that. So in this case, we added just under $2 for an added feed cost. Then the economic value that we'd use is just the difference, that 879 minus 196 gets us the 683 for at least an initial economic value that we'd use for milk protein. So most traits aren't quite this simple, but kind of just highlights how easy it can be in calculating economic value. Another example I'll go over, this is kind of a basic example that we'd use for a trait like marble score within beef. And how I like to think of creating economic values for a lot of what we do, it's kind of a what if scenario. In this case, we have the basically blue population as our base. And in this case, we have a mean of about 1.5 for marble score. And then we think of a what if scenario. What if we improve that population to a mean of 2.5 for marble score? What that does, it just shifts everything to the right. It may have changed the standard deviation a bit. In this case, we didn't. But then how do we use this to create an economic value? You can see in the base population that our premium for a 0 to 1 score is 50 cents. And in this case, we have a small but not insignificant portion of that population that only receives a 50-cent premium based on marble score. In our improved population, there's pretty much nothing below that marble score of 1. So there's nothing that's going to be only given 50-cent premium. But we have a nice chunk of our population that will receive instead of basically a $3 premium for marble score. So I don't have the formulas written out exactly, but how we would calculate an economic value given this data. It's basically getting the area under the curve, the population portion of the population that is a 50-cent, 150 or $1.50, $2 and $3 that would receive those, and we would have basically a larger expected economic response. There's economic impact for that improved population. Just take the difference between the improved and the base population, and that would be our starting economic value. So a little more complicated, but still kind of follows that same process that we went through in the milk example. This could have more additional value could be received on different aspects. There could be more costs if there's additional feeding required to put down that fat within the muscle. Basically, all of the traits that we look at, it's kind of starting out at a baseline, thinking of what's the economic positives that could come out of it, what's the economic cost, what data do we have available, and how do we put that all together to kind of come down to one number. So once we get those economic values, we have the breeding values, kind of put those all together into the formula and spit out our single selection index. In this case, looking at breeding worth, which is the national selection index for New Zealand dairy that we work with. Then on the right is one of the results of our selection index testing. This is just the emphasis of the breeding worth index of each trait within the breeding worth index. So not surprising, most of the emphasis, most of the selection pressure is going to be on production traits within dairy. Live weight has a significant portion within New Zealand as well. A little bit more important there than you could think in North America, given it's a much more pasture-based system where cows need to walk to get to their feed. A little bigger animal is going to burn more energy than smaller one in that case. But still significant amount of selection pressure for health and fertility traits as well. Another way to look at results of selection indexes here, it's just a bull list of the Canadian LPI index. Looking in specifically at a couple bulls, we're going to pick out bulls Captain and Einstein. Both of these are at the top of the list. Both of these are very elite animals. But when looking at the selection index values as well as traits, you can kind of pick out that, well, there's different paths to achieve that same or similar index value. And now as these have very similar index values, the profit their daughters will receive on farm should be very similar, just a little different path to achieve it. We can see Captain outperforms Einstein for milk, fat, protein genetics. But then on the other side, Einstein is much better for herd life, mastitis resistance, metabolic disease resistance. So it's just a different way to achieve that profitability on the farm. Daughters from Einstein will produce a bit more milk, but will have a bit more cost related to health issues, most likely. Einstein's daughters will produce a little bit more milk, but you're not going to see any issues. They're just going to be ones that you don't notice, not going to be spending cost, time, or effort treating any health problems. So getting to the next section, basically looking at some of the trends that we work with in building selection indexes and that we've seen around the globe, a bit focused on the dairy, but a lot of this applies to other species as well. So one of the biggest impacts in recent years is the addition of feed efficiency traits, feed save traits. We've seen this in Canada, US, Australia, many of the European countries within dairy. And it's probably been one of the most impactful, highest emphasis additions to selection indexes in dairy that we've seen in a long time. Lactation persistency is another thing that's beginning to be added, especially in more looked at to be included. And lactation persistency is essentially trying to maintain high milk production throughout the lactation, rather than just seeing a high peak at, say, 60 to 90 days and then a steep drop off. Another one we're looking at seeing whether being added or look to be added is heat tolerance. Working in a project in Australia at the moment with trying to get at least a specific index for a region in Australia that is more much hotter, with still a lot of dairy animals there, to create a selection index that's a bit more focused for them. Another trend that we continue seeing is focused selection. So this is area where it's pretty much new traits being added that somewhat take away from previous traits or try to provide more targeted selection. So if you look at kind of health and longevity, historically, a long time ago, type and composite traits had been all that was available for longevity. So essentially in cattle, the set of the legs, the angularity of the bones, how that animal looked was used as a proxy for survival before we had good data to be able to predict survivability in an adequate manner. Then we had inclusion of traits such as productive life in the US, herd life in Canada, and these are kind of all-encompassing health traits. So this is a trait that measures how long an animal stays in the herd. So everything impacts how long an animal stays in the herd, whether it's production, reproductive ability, disease traits, diseases, things like that. And as we've progressed more recently, started to move back a little bit from that all-encompassing survivability trait to adding very specific traits. So things like a heifer livability, looking at specific diseases like milk fever, displaced abomasum, ketosis, metritis, in trying to more target that selection to either improve or make sure disease resistance for cattle in these specific areas do not decrease. Same thing on the calf side, calf livability, traits such as respiratory disease, scours, included in Zoetis indexes in the US, with current project looking to include those into Canada. Project we work with in Poland, looking at adding digital dermatitis, trait that had been recently added in Canada, and removing some of that selection emphasis away from feet and legs. So we see similar within reproductive traits. So within the US, what we've historically selected on for reproduction has been DPR. Recently been addition of a bit more focused selection, earlier first calving, heifer conception rate, cow conception rate, trying to look at very specific portions of that reproduction. Work at University of Wisconsin, I believe there's some at Guelph too, even looking at further stages, whether it's maintaining the embryo through 30 days, 30 to 60 days, things like that have the potential to be included as well. Also specific fertility disorders, such as cystic ovaries, things like that. Abortion, twinning, gestation length, go into kind of an example within the New Zealand dairy, whether you think of repro as an actual, or gestation length as an actual reproductive trait, but it definitely has correlations depending on how you measure it. But something we see continually in work that we do, and work that we see around the globe, just trying to develop the new traits that more target that selection. Then within selection indexes, getting the economic values for those specific traits and trying to tease those out of the broader traits. So an example of this that we've done in New Zealand, at least colleagues that I've worked with have done in New Zealand, is separating out fertility and gestation length. So historically, until very recently, the fertility trait in New Zealand was called calving season day. And this was the interval between the planned start of calving and the cow's calving date. And this can be impacted by many different things, how fast they come back into heat after calving, their conception, any embryo survivability. And it's also very highly correlated with a trait that has a higher heritability in gestation length. And what they had seen through data is that selecting through this fertility trait saw a fairly large decrease in gestation length and less of an improvement in actual fertility than they were hoping. So essentially work was done to define a fertility trait independent of gestation length. Basically requires different data, different analysis. I think making sure you have the correct data was the biggest aspect for the group here, but definitely seen as important to disentangle these two traits. And in talking about selection indexes, what was done, disentangling these traits allowed us to create economic values for both of them. And it allows for more targeted selection and targeted monitoring for both the fertility and the gestation length independent of each other. And so what the table on the right is showing is the Breeding-Worth 2022 index. And this would be the one when they were still combined. And the Breeding-Worth 2024 was when they were split out. And this is a response in economic units, so in New Zealand dollars. And what we can see with the fertility and gestation length, that once they were separated out, the expected response or the expected increase in value we get by using this selection index increased for both of these traits once we had that more targeted selection. So we do see more genetic gain in gestation length. Definitely was discussion on if we want to continue pushing that gestation length down. I think there's always the thought that pushing it too low could bring in some negative side effects. Definitely still a discussion within New Zealand as they update index year after year. So next, getting into work we've done in the dairy beef space. So breeding beef bulls to dairy cattle has been around about a decade or so now, especially after the development of sex semen. Initially, when dairy producers were interested in using beef cattle, the main thing they were interested in is beef bull that will get the cows pregnant and won't cause any calving difficulties. For dairy producers, beef producers, after a while, realized that, well, there's a bit more that needs to be done in selection of beef animals. And so what we've done with both American Angus, as well as what's currently in development with Beef and Lamb New Zealand, is develop basically a whole profit index that can be used for selection of beef bulls. So for American Angus, we have two separate indexes developed, Angus by Holstein and an Angus by Jersey, selecting bulls to be bred to either breed. And then also been working in dairy beef index for Beef and Lamb New Zealand. This one is currently in development, but will provide a bit of information today. So for American Angus, this was the results of the project. You can see selection emphasis for the Angus by Holstein on the left, Angus by Jersey on the right. And when selecting these bulls through economic values that we developed, bulls basically need good calving, so not ignoring the dairy producer's needs. Still need to make sure that the bulls aren't going to cause any issues on the dairy farm. Other things that the beef bull is going to need to bring, good muscling. This is kind of both more muscling and better shaped muscle. So dairy animal hasn't been selected for muscle shape at all. And what has happened is a lot of those loin eyes and steaks within a Holstein animal or Jersey animal gets to be more flat and elongated and not kind of a circular shape that is more desirable at a restaurant for a beef animal. So one of the decisions in the selection index development here was to try to make sure the beef animals bring a little more rounded steak to the genetics. Shorter height is a very big one, especially on the Holstein side. Anybody that's been recently next to a Holstein and a Jersey definitely notices the height difference. Not an enormous issue on farm, but when you get to the slaughterhouse, very big Holstein animals and very big Holstein by beef crossbreds can have issues if they're on the rail and too tall and are being dragged on the ground. Sanitary issues, time effort to adjust things that can be helped within selection index development. Another thing, faster growth. Dairy cattle aren't directly selected for faster growth, kind of comes a little bit, but you see the dairy cows still growing 24 to 36 to 40 months of age, whereas the beef animals try to produce that more mature size 18 to 25. So definitely looking for the Angus animals to bring a little more growth to the beef. So when looking at development within New Zealand, very, very similar. Still want to get that calving ease, very high or decently high proportion, but definitely not the entire index. Again, carcass traits are very important within the crossbred, very much for the same reason we talked about within the Angus. And growth and a few other traits. Other traits here include docility as well as gestation length. Talked a little bit about the gestation length on New Zealand dairy in the previous section. For the beef animals, it's actually even more important to have short gestation length because in this case, the beef on dairy in New Zealand would be the third, fourth, fifth matings. And these are the ones that really need that extra emphasis to get back on track within that seasonal grazing period. So if basically, if a dairy cow calves too late, it's going to miss the high quality feed time as everything's on pasture. There's nothing brought to it, and they all get cut off, dried out at the exact same time. So a late calving animal is going to miss the quality feed, and its lactation length is going to be greatly shortened. So one thing somewhat interesting that we do within calving ease for the dairy beef especially, but within beef as a whole, and even on the dairy side, is incorporate nonlinear economic values. So if you think back to the formulas I presented, it was pretty much a economic value multiplied by the genetic value, very much a linear 1 unit change in genetics equals a 1 unit change in that economics. But for nonlinear traits, what essentially we're trying to do is to enormously penalize those with extremely poor calving ease. You see on that -10 to -25 portion. But on the horizontal set axis here, when we get up to 0, 5, 10, these are all sufficient. They're not going to produce calves that are going to have calving difficulties. So by the time you get to -5 breeding value or a 0 breeding value, there's not more improvement that you need to be making. It's not going to cause any problems. We want to put selection on other traits at that point, and avoid basically unnecessary selection on a trait that's not going to make an impact. So basically for both the American Angus and the New Zealand beef and lamb index, incorporate distributions like this, where the extremely poor calving bulls will have an enormous impact on that single economic or that index value, and the moderate to okay ones will have essentially no impact. So this is a type of process that can be done for several other traits as well. It takes a bit more monitoring through the years and a lot more effort to create, but can be very useful. Another one we use this for is in lodging in crops. So if you think corn and soybeans, lodging is essentially that crop's ability to stand up in the field in normal and adverse weather conditions. So basically, it's the strength of that stem to withstand high wind, high rain, things like that. And there's a point where that stem is going to be strong enough that you don't need to put more selection emphasis towards that. But anything below that has a likelihood of falling down, ruining the harvest, you need to make sure that's not included in the final indexes. Another one within dairy and beef that I think has the potential to use this, but is definitely not there yet, would be fertility. You can very much think of a situation in dairy where enough animals are pregnant after 1 or 2 services that produce more than a sufficient amount of replacements, that you don't need to improve that much more, and you can put more emphasis on health or production traits or emissions traits, things like that. But those that are very poor, you want to make sure that they are penalized efficiently. Definitely not there yet, but to me, one that could be in the future. To finish up, talk a little bit about work that we've been doing and has happened, I think, at CGIL, at plenty of other places looking at emissions. So one thing we can do with emissions in selection indexes is basically either include a methane trait, as has been developed in Canada, or basically simulate methane trait based on correlations with others and investigate the impact that trait could have on selection progress, selection response. Another thing we can do without traits like methane or CO2 equivalents would be just estimating the change in given genetic selection on the traits for methane or CO2 equivalents. And I'll give an example in the next slide in that case. Or we can just basically have the selection indexes we have now. We look at the changes in feed, changes in survival, things like that. What's impacting emissions? How are the genetic changes happening with those selection indexes, and how do those relate to emissions? So basically, what we can do within selection indexes is kind of just reconfigure that selection index formula that I had shown earlier and change that to an outcome of purely genetic economic response to a CO2 equivalent or a methane response. So in this case, it's basically looking at using the same input data, same change in feed, change in survivability, and instead of ending up with a economic value, we're ending up with a single unit that is a change in methane or CO2 equivalent per that change in breeding value. Then if we go through an index testing and we say, in this case, for the index, we gain $150 per generation with our selection index, but we increase methane emission by X amount. So what if we made a few adjustments? Now we're going to increase our genetic or our economics by say $140, but we're going to have a less increase or a neutral response for methane. It's kind of the what we're looking for within these two indexes. So with that, we can either look at emissions intensity or gross emissions. A lot of these are kind of dictated by the groups we work with. Could be government organizations want to look at a specific one, or groups we're looking at want to focus on specific aspects. So this formula here is showing formula for producing emissions intensity from a cow. So basically every greenhouse gas they emit, whether it's through a replacement age or as a mature cow is in the numerator. And that is just divided by their production, whether that's milk, whether that's meat. And so the emissions intensity is a change in greenhouse gas per unit of output, milk, meat, wool in case of sheep. If we want to look at just gross emissions, we would ignore the output and just focus on the greenhouse gas that they produce. Can be a little bit more dangerous to do the later. Example that I've seen provided is that just focusing on gross emissions can say that calf health should be really poor, because if all the calves die, well, there's nothing to grow up to produce emissions. And as animal breeders, you don't really want that. Want to make sure it's adequate for the animal industry and not just removing the animal industry. But both can have their positives and negatives, and both need to be, we do projects with the goal of either emissions or intensity, just needs to be understood in either manner. So a couple examples of this work. On the left is PhD work from a colleague of ours and previous colleagues of yours at CGIL and Chaley Richardson. And what this is showing is a response in carbon dioxide equivalents as well for key traits in the Australian index, as well as a response to selection for those traits. So we can see the changes due to selection for fat, protein, and milk volume increase the CO2 equivalents produced. The changes, the genetic gains for survival and feed saved, will reduce the CO2 equivalents produced. On the right-hand side, example of a group in the UK created an EnviroCow PTA index. And what this is showing is just decile rank based on their EnviroCow index. And what it's showing is the top animals produce the most milk, while also the least amount of methane. So there's definitely trade-offs between production and methane, but it has achieved a level where, yeah, we're still going to improve milk production. It's going to be at a lower rate, but the methane emissions are not going to increase at the same rate or same level that they have without including a methane trait within. So that's basically what I had to discuss today. To thank a lot of all the partners that we worked with for the data. Thanks for your attention. Glad to take any questions.
Thank you very much, Doug. That was a wonderful presentation. We'll now open the floor to questions either online or in the room here. If you're online, you are welcome to turn on your camera and your microphone to ask a question or message in the chat. But I think we have a question here in the room.
Hello, Dr. Dog. First of all, thank you for our presentation. Nice presentation. Here's Bruno. I would like to ask you for the economic value calculations. Who is going to be involved in this calculation? I mean, check how much food a cow eats, or the price of the crops to get this value, and how much more that milk will be paid for, or that meat will be paid for. So our economist is a economist people that is involved in this part, or you grab this information from official government websites? So this is my question. Thank you.
Very good question. What we try to do with the groups that we work with is they have either on staff that gather that information, and that's best possible from economists or published sources that they have, such as, say, within New Zealand, Fonterra is the biggest milk producer. We talk to them, our groups talk to them, what exactly are they paying for milk? What is the different prices? What are the different costs? Try to go to nutritionists on the cost. What is the feed cost? You kind of need to make some assumptions. If we can't get it from sources like that, go down to published literature if we need. veterinarians on some of the health costs. Basically, anywhere we can get as exact as possible. But sometimes you can't and have to make assumptions. Sometimes you need to use data from different breeds. That's kind of part of the reason to also go into the consultation with farmers and stuff to make certain, especially if you don't have the really good data to go in, that it's modified to a level that's acceptable.
Just one additional question. If you have a trait, I don't know if you have that, it's not possible to estimate an economic value. I don't know. For example, methane emission, not Calvin is, but some trait it's tough to get the economic value. Can you replace for another index? For another value?
Yeah, we do that for some traits, yes. There's a lot, especially type composite traits in cattle can be very difficult because it's difficult to get some of the correlations between what you're trying to estimate. And yeah, it can be very difficult. And some of those, like methane, will do tests like sensitivity analysis on potential prices that could be included. Whether that's one of those ends up in a finalized published index that we're using is kind of up to our clients. But a lot of those that we don't know, yeah, we'll do some sensitivity. We'll try to find something related to that as possible. Go into data and try to see correlations between, say, survivability and stature or set to the legs trait, things like that. See if there is correlation and try to set that up in a manner. But yes, one of the difficult things in building selection indexes is situations like that.
Thank you very much.
Thank you. I think we have another question here in the room.
Hi, I was wondering if you could expand more on the index that's created for developing countries and which traits are typically prioritized, or if there's anything interesting that these countries prioritize compared to others.
Yep, that's a good question. And one of the difficulties we see in some of the developing countries too is there's not a good pipeline for the genetic evaluations. So sometimes it ends up being more phenotypes and trying to clean those as good as possible and making the index as simple as possible. Whether it's you try to avoid just a production trait, try to get something on the fertility, something on the survivability, just to make sure we don't start them down the same road we see in North American dairy where fertility drops off because we've only selected for production. But yeah, very unique situations, but trying to keep it as simple as possible has been, I think, our goal within the developing countries.
Thank you.
And just a follow-up question to that, when you are looking at developing indices in developing countries, are you generally looking to source genetics from within the country, or are you often looking to bring in genetics from like North America or Oceania?
Maybe a bit of both. What we're looking at in India might depend or might be a bit of both of what you suggested. They do bring in some genetics, but there's enough within internal that based on preferences need to have selection for, and they're not just going to 100% change and probably shouldn't 100% change to imported genetics. So yeah, definitely try to include both, but some of it depends on the locale too.
Yep. Do we have any other questions from online or in person in the room here? I'll ask another question. What is the average number of traits that you're looking at fitting in a lot of these indices? Is it generally closer to over, a couple dozen, or is it smaller?
We try to work with about 10 to 15 in most indexes. because within ours, we try to put a decent amount of time into each trait. And especially if there's nonlinears, some of them can get very complex and it's just time consuming. I think within our, some of our crops get up to about 20, but try to avoid putting too much in. At that stage, some of what we do within the index testing is monitoring the traits that aren't included. So as I talked about kind of the more targeted selection, what you can also do is say, these traits aren't in the index, but let's make sure we're monitoring them and what the index should be doing to those traits. So it's not necessarily putting the effort to put them in, but making sure we're still on the right course.
Nice. Thank you very much. I'll ask again if there's any questions online or in person here. It looks like you've answered everybody's questions. So thank you very much. It's been a great discussion and a wonderful presentation. It was very interesting to learn about the selection indices that you guys implement. Thank you very much for your presentation. This recording will be posted to our YouTube and we'll send you all of that information. And please come back next week for another presentation. Thank you very much.
Thank you all for listening.
Thanks.